Hello, my name is Jonathan. I'm a member of Statistics Without Borders. I'm from San Jose, California. I'm a full-time data scientist and a part-time R and statistics tutor. And today we're going to be talking about vectors in R. Now, vectors are a fundamental data structure in R. You can think of them as simply an ordered list of things. If you're at all familiar with Python, it's very similar to what they might call a list. And if you're at all familiar with more old school programming languages, it's very similar to what they might call an array. It's all kind of the same idea, just an object that holds other objects. There are three main types of vectors in R, and this lecture will be split into three parts accordingly. First, we're going to talk about atomic vectors, which are the most common basic types of vectors. And then we're going to talk about what are called recursive vectors, such as lists and data frames. And finally, we're going to talk about augmented vectors, such as names, factors, dates. So let's get started with atomic vectors. Atomic vectors are the most basic type of vector. So like I said earlier, they're just, you could think of them as a list of objects. But one thing to keep in mind is that all of these objects need to be of the same type. Some common types in R are numeric, which are just numbers, character, which other languages tend to call strings, and logical, which other languages tend to call Boolean. So logical values are either true or false. So a vector needs to have all of the same type. So that means you can't have a vector which has some numbers and some characters. It needs to be all numbers or all characters or all logical. There are some other less common types such as complex and raw, but those won't be covered in this lecture. So how do we declare a vector? The most basic way to declare a vector is with this C parentheses notation. So you put the letter C and then you put some open and close parentheses, and between the parentheses you separate things with commas. So this would be an example of declaring a numeric vector. This would be an example of declaring a character vector. If you want to declare a vector which is an integer sequence, then a very handy trick is to use the colon notation. So if you put a number, a colon, then another number, it just counts from the first number to the second number. So notice you can either go forwards or you could go backwards by saying 3:1, and then it'll give you the vector 3, 2, 1. So those are the basics, but say you want to make some more complicated sequences. I'm going to give you two fundamental functions for creating numeric sequences. The first is REP, which is short for repeat. So as you might imagine, it lets you repeat things. So say I wanted to repeat 5 3 times, and you would get the vector 5, 5, 5. The first argument can also be a vector itself. So say I want to repeat the vector 1:3 3 times. So it gives me 1, 2, 3, repeated 3 times. If you want to repeat each element and not necessarily the entire sequence, then you could use the argument each. So if I say repeat 1 through 3 each 3 times, then it gives me 1, 1, 1, 2, 2, 2, 3, 3, 3. So that's very handy. The next function I want to tell you about is SEQ, which is short for sequence. So this is handy when you want to declare some more complicated sequences. So if I wanted to go from 2 to 10, I could just say 2:10. But say I didn't want every number, I only wanted every other number. So that's what I would use SEQ for. You could say I want a sequence from 2 to 10 by 2, and it gives you 2, 4, 6, 8, 10. You could also count backwards. So you could say I want a sequence from 10 to -10. But notice here I have to say -5. I can't say 5. If you just say go from 10 to -10 by 5, R will say, I don't know how to do that. I can't count backwards using a positive number. So you have to be careful about the sign here of your by argument. But here I say I want to go from 10 to -10 by -5, and it gives me 10, 5, 0, -5, 10. You can also create non-integer sequences. So you can specify the by argument can, if it's a decimal number, then it'll give you a sequence such as this. Like if you want to go from 0 to 1 by 0.1, it'll give you this sequence. You could also, instead of specifying by, you can specify length out. So say I want a sequence from 0 to 1 in equal steps. I don't know exactly what that step is, but I know that I want the entire sequence to be of length 18. So you could say I want to go from 0 to 1, length out is 18, and this is the resulting vector. So here are some exercises for you to try. I encourage you to pause the video and try this yourself and resume it when you're ready to see my solution. Okay, so hopefully you've given these a shot on your own, but let's take a look at these. So first I asked you to create a vector of 4 4s, 3 3s, 2 2s, and 1 1. So something to know is that inside of the C parentheses, you can also put other vectors. You can combine, let's say, this vector and this vector to give you this vector. So that's sort of what I'm going to do here, but I'm going to use rep. So first we want to repeat 4 times. We want to repeat 3 times. We want to repeat 2 times. And then we just want a 1. So this should be the vector that I was asking for. And then on the next one, it looks like we want to use sequence and we want to use length out. So I want a sequence from 0 to 2 pi. Length out equals 25. And this final one looks a little complicated, but looking at it, you can break it down into smaller chunks. So see that this portion repeats twice. So we know we want to repeat something twice. We just need to figure out what that something is. And then we can break down the something into smaller parts. So first we have 3 3 2 2 1 1. Well, we could use repeat for that. So rep the sequence 3 to 1, each element twice. But we want to add something to the end of that. So let's put that inside of a C parentheses. And then let's just do these two things separately. So we have 3 -2s. So we want to repeat -2 times, and then we want to repeat -1 twice. So this should be the vector that I was asking for. Okay, now let's talk about indexing. Indexing is hugely important. In R, we use square brackets. So say you want to grab the first element of a vector. So here I have a vector x. If I say x square bracket 1, it gives me the first element. If I say x and then square bracket length of x, this gives me the last element, because length of x just tells you how long it is. So this, this vector is 7 numbers long. So the 7th number is 9. Notice a lot of programming languages start with 0 indexing. R starts with 1 indexing. So the first element is element 1, not element 0. That's important to keep in mind. Another thing to know is that you can also use a vector to index another vector. So here I'm using the vector 1 3 5 to index this vector x, and it gives me the first element, the third element, and the 5th element. And you can use all sorts of crazy vectors you want. Like here I'm using rep to repeat these elements some number of times. Another thing to know about vectors in R is the way that mathematical operations work is what we call vectorized. So that means that if you apply some mathematical operation to a vector, it performs that operation element-wise, so element by element. So what I mean is if I have this vector and I add a half to this vector, it adds a half to each element individually. Similarly, if we multiply a vector by 2, we're multiplying each element by 2. And here, same thing, I'm just raising each element to the power of 2. The vectorized operations can also happen not only element-wise, but also what is called pairwise. So if we have 2 vectors of the same length and an operation in between them, then it performs that operation pairwise. So the first element of this vector raised to the power of the first element of this vector. So 1 to the power of 5 is 1, 2 to the power of 4 is 16, 3 to the power of 3 is 27, and so on. So here I'm adding 2 vectors together. So it adds the first elements, it adds the second elements, and it adds the third elements. And we get the vector 11, 22, 33. And here is another way to do the exact same thing. I'm using the colon notation and then I'm using sequence, but the resulting vector is exactly the same. And then here is yet a third way to do the same thing. So I'm showing you that in programming, oftentimes there's more than one valid way to do something. this third one's a little bit interesting. Notice that there's sort of an order of operations thing happening here. So I have this vector 1:3, and I'm multiplying it by 10. So that multiplies each element by 10. So we have 10, 20, 30. And then to each of those elements, I'm adding 1, 2, 3. Let's talk about comparators. So a comparator is something like greater than, less than, equal to. Notice the double equal sign is how you ask, is something equal to something else? So when you use a comparator, you're going to get a logical value. Or if you apply a comparator to a vector, you're going to get a logical vector. So this right here is asking, for each element of this vector, is that element greater than 5? So everywhere that it's greater than 5, you'll see true. So 8 is greater than 5, 6 is greater than 5. And everywhere that it's not greater than 5, you'll see false. So 5 is not greater than 5. 3 is not greater than 5. In the next example, I'm using what is called the modulo operator. So basically, it takes a number and it takes away the second number from it as many times as it can, and then it asks what's left over. So it's a very common way of checking if a number is divisible by another number. So if a number mod 2 is equal to 0, that means that that number is even. That number is divisible by 2. So this is basically asking, from this vector, which elements are even? So we can see that the first element is even, the second element is even, and so on. And you can also perform operators on not numbers. You can perform them on characters. So here I'm asking, in this vector, which elements are equal to the string C? And we can see that the third element is, and the other ones are not. You can also use comparators pairwise, similar to how we used operators on the last slide. So here I'm asking, for each pair of elements between these two vectors, which ones are equal? So first it's asking, is 1 equal to 3? The answer is no. And then it's asking, is 2 equal to 2? The answer is yes. And then it's asking, is 3 equal to 1? And the answer is no. A similar thing is happening here. This is asking, is 1 less than 20? The answer is yes, etc. Logical vectors have a nice property that if you try to convert a logical value to a numeric value, it will turn all the trues into 1 and it will turn all the falses into 0. Why is this useful? Well, oftentimes with a logical vector, you might have some questions about it, such as how many of these are true or what proportion are true. And this is pretty easy to do then with using a sum function or a mean function. So for example, here I'm applying sum here to say how many of these values are greater than 2. And it turns out that 5 are greater than 2. And here I'm asking what proportion of these values are greater than 2. And it turns out that the proportion of values that are greater than 2 is 0.625. Earlier, we talked about using numeric vectors to index other vectors. And you could do sort of the same thing with logical vectors. But notice here, there's a key difference that with numeric vectors, the vector you're using to index doesn't have to be the same length as the original vector. But here, it only makes sense if this vector is of the same length as this vector, because each logical value refers to a certain index of the original vector, and it tells it whether you want to keep it or not. So if it's true, you keep it. If it's false, you don't keep it. So here I'm saying I do want the first value. I don't want the second value. I do want the third value. I don't want the fourth value. And I do want the fifth value. So that's why I get the vector 1, 3, 5 when I run this. But oftentimes when you're using logical vectors to index other vectors, you're not literally creating a logical vector like true, false, true, false. Usually you're using some sort of comparator. So here I'm asking, give me all of the values of this vector which are odd. So give me all the values for which that value mod 2 is equal to 1. And it gives me all the odd numbers, 1, 3, 5. And here I'm saying, for all of these values, give me the values which are equal to 2. And it gives me the number 2. Oftentimes, you might want to know what indices contain the value, the true values in a logical vector. And that's what the which function is useful for. So here, I'm asking, which indices of this vector contain a number which is greater than 3. So we can see that the first, second, third, fourth, and seventh indices contain a value which is greater than 3, and the fifth and sixth index do not contain a value which is greater than 3. Similarly here, I'm asking which index contains a value which is even. And we can see that the first value is even, the second value is even, and the sixth value is even. I want to tell you about two more functions that are very useful when dealing with logical vectors, the all function and the any function. So sometimes when you have a logical vector, you don't particularly care about each individual value. You kind of care about the vector in an aggregate sense. So are all of these true, or are any of these true? So if you have a question like that, then these functions are very useful. So here I'm asking, are all of these values true? And the answer is no, they're not all true. The last one is not true. Here I'm asking, are any of these values true? And the answer is yes, some of them are true. At least one of them is true, so it returns true. And here I'm asking the same thing, are any of these true? And it returns false, because no, none of them are true. So here are some more exercises for you to try. This time, I'm giving you three lines of code, and I want you to guess what they will return without running them. So for each one, I want you to think about what will this line of code return, and maybe try running it on your own and see if you're right. And so pause the video now, think about it, and resume the video when you're ready to see the answers. Okay, let's take a look at these lines of code. I think it's a good exercise in general to think about what a line of code will do before you run it. And a good strategy is to think from the inside out. So what I mean by that is we have something inside of a function. So let's think about what the thing inside the function will do first, and then think about what the function will do given this as an argument. So first we have a vector 1 through 10, and we're comparing it to the number 5. So for each number 1 through 10, is it greater than 5? So it says false, 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 true, 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 true. Because 6 is greater than 5, 7 is greater than 5, but none of these numbers are greater than 5. And then we're asking, are any of these logical values true? And of course, the answer is yes, some of them are true. Not all of them are true, but that's okay. We just want to know, are any of them true? So this line of code should return true. So then for the next one, we're asking, are all of these values true? And this is the same as what was on the inside last time. So we know that not all of them are true. Some of them are false and some of them are true. So this line of code should return false. And finally, we're asking, are all of these numbers greater than 0? And the answer is yes, all of these numbers are greater than 0. So this should return true. So far we've talked about numeric vectors and logical vectors at length, and we've touched on characters, but let's talk about character vectors. I want to give you 4 really useful functions that you can use when you're dealing with character vectors. The first one is paste. So say you have 2 character strings that you want to paste together and turn into one single string. Or in this case, what we have is a character vector, and I want to combine it down into a single character string. So we use the function paste. We give this vector as a first argument, and then we tell it how we want it to collapse those strings together. So I put just a string with a space in it. So that I'm saying, put these together and put a space between each one of them. And that's what it gives me. String split is sort of the same idea, but in reverse. So you have a single string and you want to split it into its individual elements. So I give it this string and I tell it to split it based on a space. So this could be any string you want. In this case, I'm saying the split is a space. So it's giving me each word individually. So this is a vector of words. If you notice these double square brackets here, this means that what this function is actually returning is a list. And we'll talk about that in the next section. So don't worry about that right now. The next function is Gsub, which is useful when you want to replace elements of a string with something else. So for example, here, I'm saying, here's a character vector, and I don't want there to be any exclamation points. So replace the exclamation points with just an empty string. So it's valid to give it an empty string as an argument, you could also say replace the exclamation points with question marks or whatever you want, whatever other string you want. So what it gives me is the same character vector, but it's replaced all of the exclamation points with blank. And finally, we have the grep family of functions. This is useful when you want to find certain things in a string, in a character vector. So here I'm asking it to find the elements of this vector which contain this substring, so that just the character O. And it's telling me that the second element of this vector and the fourth element of this vector contain an O. So that's the default behavior, is just to tell you what the indices are of the elements that contain the substring. But you can also supply, if you didn't want the indices, you wanted the actual values, you could supply the optional argument value equals true. And we see this is the same exact function call, except for this value equals true here. So instead of giving me the indices, it's giving me the actual values, the second element and the fourth element. There are some other useful functions when dealing with character vectors, and I encourage you to look these up on your own time. They're mostly self-explanatory, like changing lowercase to uppercase, finding substrings, things like that. And if you're dealing with strings a lot, I would encourage you to look up a package called Stringer, which is part of the tidyverse family. The tidyverse family is a family of packages that are extremely popular. Every data scientist who uses R uses tidyverse, more or less. And here are some other packages that are included in tidyverse that you could look up in your own time. All right, let's take a look at these lines of code. So again, I think inside out is a good strategy. So let's think about what this function will do on its own. So we're taking the numeric vector 1 through 9 and trying to paste 0, 0 at the end of it. So paste wants to deal with character. So it's going to automatically convert these numbers to character. And it's just going to add 0, 0 to the end of each one. So we're going to have the character strings 100, 200, 300, and so on all the way to 900. So this is the result of the paste function. And then as.numeric is saying, take each of these character strings and convert them to numeric. So that's exactly what it's going to do. So we can tell these are not character strings because they don't have quotes around them. The next one might be a bit surprising, so don't feel too bad if you got this one wrong. So why doesn't it, let's see what it does. So why isn't this the character string true? Because we're just telling it to turn this vector into a character string. Well, recall that a atomic vector needs to be homogeneous. Every element needs to be of the same type. So the first thing that we're doing is that we're creating this vector. So when we create this vector, it's not legal to have some logical values and some numeric values. So it's going to automatically cast certain types to other types to make it so that the entire vector is of one type. And there's a hierarchy of types that it prefers to other types. So in the presence of any string, so let's say that we turn this into a character, it'll convert everything to character. So even this false value turns into the word false. But in our example, we didn't have any character values. So character is its preferred type, and then numeric is its second preferred type, and logical is its least favorite type. So when you have a mixture of logical and numeric, it's going to try to convert everything to numeric. So indeed, it converts true to 1, and it converts false to 0. So this is the vector that we're supplying as the argument to this as.character function. So when it converts this vector to character, it simply turns this into the character string 1, and so on. So that's what we see here. So for the next one, if we go inside out, there's quite a few things going on. So let's start with this rep. So we're repeating the numeric vector 1 through 3, each element twice. So 1, 1, 2, 2, 3, 3. And then we're applying as.character to it. So that looks like this. We're just turning these into strings. And then there's a comparator. So we're asking, are any of these character strings equal to the character string true? And notice this is not a logical value. This is a character string because it's inside of quotes. So are any of these equal to the character string true? No. So this should return false. Let's look at the last one. So again, the inside, starting at the inside, we have a paste function. So we're pasting the two numeric vectors 1 through 3, and we're separating them by a decimal. So again, paste likes to deal with characters, not numbers. So it's going to convert these to character strings. So it's going to be 1.1, 2.2, 3.3 as strings. And then we're converting that to numeric. So it's going to be the doubles, 1.1, 2.2, 3.3. And then we're multiplying each of those values by 100. So it's going to be 110, 220, 330. And then we have a comparator. So we're asking, for each of these values, is it greater than 100? And yes, they are all greater than 100. So it should say true, true, true. And then finally, we're asking, are all of these values true? The answer is yes. So this should return true. So part 2 of this lecture is on recursive vectors. You can think of recursive vectors in some sense as vectors of vectors. That's why they're called recursive. So the first type of recursive vector we're going to talk about are called lists. So lists are very similar to vectors. One big difference is that, recall, atomic vectors needed to be homogeneous. They needed to contain all the same type of thing. And that's not true for lists. Lists can contain any type of object, and not just single values either. So lists, you can have a list of lists, you can have a list of vectors, you can have a list of functions, and you can mix and match as well. So you could have a list that has a function and a data frame and a vector. So anything you want, you can put inside of a list. So when we talked about atomic vectors, we talked about indexing. We use single square brackets to index an atomic vector. And similar idea here, but with lists, we use double square brackets. So here I'm creating a list of 4 elements. The first element is the vector 1, 2, 3. The second element is a data frame called iris, which is built into R. The third element is this is a logical vector. So we're taking each element of this column of iris and we're asking, is it bigger than 6? And the fourth element is a function, the mean function. So when I say my list bracket bracket 1, I'm asking it to give me the first element of this list, which is the vector 1, 2, 3. And notice this element is a vector itself. So we can ask for the second element of the first element of my list. And it gives me exactly that, the number 2. So here's an exercise on recursive vectors. I want you to think about this list this example list that I just showed you. And I want you to tell me in English, what will the following code return? So first, if you haven't heard of iris before, I would just look at iris, see what it is, and then think about what this line of code will return, and unpause the video when you're ready to see the answer. Okay, let's take a look at this. So you may notice that here we have the third element of my list, which is a logical vector, and here we have the fourth element of my list, which is a function. And you may be wondering, what are these parentheses doing here? So right off the bat, when you see these parentheses, you should be thinking the thing on the left of the parentheses is a function, and the thing inside the parentheses is an argument to that function. So the question is, what in English will the following code return? Well, if you had said something like the function that is the fourth element of my list applied to the third element of my list, I would give you partial credit for that. That is technically true, but it's not exactly what I was looking for. So if you recall earlier when we were talking about logical vectors and finding counts and proportions of logical vectors, that's what's happening here. So we're finding the mean of this logical vector. So in English, we're finding the proportion of flowers in the iris data set, which have a sepal length that is greater than 6. So it turns out that about 41% of flowers in the iris data set have a sepal length greater than 6. So that's what I was looking for. Let's talk about the str function. Str is short for structure. Now it's very useful when you want to look at the structure of an object, particularly some sort of recursive vector. So here we're looking at the structure of my list, and we can see that it is a list of 4 elements, and it tells me what all of those elements are. So first we have a numeric vector, then we have a data frame, and it even shows me the structure of that data frame. And then we have a logical vector, and then we have a function. So it's very, very useful when you have some mystery object and you want to look at what's inside of that object. Here's an example of one such mystery object, a linear model object. So it turns out that fitted linear model in R is stored as a list, so we can use str to see what's inside of it. So here I'm fitting a linear model on sepal length as a function of sepal width. My data is iris. And then if I look at the structure of this fitted object, I see that it is a list of 12 elements, and it tells me what all the elements are. And notice this time, these elements actually have names. So we have coefficients, we have residuals, we have effects, and so on. So when these elements have names, we can access them by name using the $sign. So if I say fit $sign coefficients, it gives me the coefficients from the model. And you could achieve the same thing using the square brackets like we talked about. So fit double square bracket 1 gives me the first element, which happens to be this element. Let's talk about data frames. So we've already seen a data frame, namely iris. A data frame is a special case of a list. Each element of the list is a named vector. These correspond to the columns of the data frame, and each vector has to have the same length. So the length of each vector corresponds to the number of rows in the data frame. So here we're taking a look at the structure of the iris data frame, and we can see that it has 150 rows, 5 columns, and then we can see what all the columns are called. We can see how they're stored. So the first 4 columns are all numeric, and then the last column is a factor. And we'll talk about factors in a little bit. So here's another exercise for you to try. Again, in English, I want you to tell me what the following lines of code will return. Okay, hopefully you had a chance to try this on your own. Let's take a look. So if you recall, I mentioned that data frames are a special case of a list. So technically iris is a list. So we can use the double brackets to ask for the first element. In the case of a data frame, each element is a column. So when I ask for the first element of iris, I'm asking for the first column of iris, and that's what it will return. The first column is a numeric vector. Here's another way to deal with indexing when it comes to data frames. So we use single square brackets and then a comma in the middle. And anything before the comma tells it which rows to select, and anything after the comma tells it which columns to select. If you leave it blank, it means I want everything. So here I'm saying I want all the rows, but I only want the first column. So again, this is going to return the first column of iris. The first column of iris has a name. It's called sepal length. So we can ask for it by name using a $sign. So we can say iris $sign sepal length, and it will give us the first column of iris. Here I'm using the square brackets with a comma, but instead of asking for an index number, I'm asking for a name as a character string. So here I'm asking for the sepal length column of iris. So once again, this will give me the first column of iris. And here we're using the double bracket notation, but instead of the index number, we're asking for a name. So once again, this will give me the first column of iris. So perhaps surprisingly, all 5 of these lines of code do the exact same thing. They're all perfectly valid ways of asking for the first column of iris. In the final part of this lecture, we're going to be talking about augmented vectors. So sometimes a vector will have other information stored in it other than the raw data. So this is known as augmented vectors. Let me show you what I'm talking about. So as an example, vectors can have names. We've already seen that lists can have names, so each element of a list can be named, but the same is true for atomic vectors as well. So each element of a vector can have a name. A very common example of that would be the output of a table function. So say I ask for a table of the species column of iris. So basically what it's going to do is it's going to count how many times each species appears in the iris data set. So each species appears 50 times, so we see 50, 50, 50. But so that we know which species each number belongs to, each number has a name. Each element of this vector has a name. So these are the names of this vector. A named vector behaves just like any other atomic vector, so we can perform mathematical operations with it. We can ask for the first element. So here I'm asking for the first element of this named vector, and it gives me the first element. You can use a function called names to either access or overwrite the names of a named vector. So as an example, let's go back to our fitted model object that we created earlier. So if we say fit $residuals, it gives me a named vector where each element is the residual is a residual from the model, and along with it is a name, which is the index in the original data set that residual belongs to. So if we use the names function, we can get the names of this name vector as a vector. And notice that it's a character vector, even though the names here, they look like numbers, but they're actually not numeric. They're stored as characters. So that's the result that you see here. So here we're asking for it to give us the names from this named vector, but we can also use the same function to overwrite the names. We can say the names of this named vector are equal to something, and then we tell it what that something is. So here I'm using paste to put this character string before all of the numbers 1 through 150. So it's going to say residual number 1, residual number 2, and so on. So I'm overwriting the names, and then when we look at the vector itself, we can see that it now has these new names. So here's an exercise I want you to try with augmented vectors. Pause the video and give it a shot, and resume when you're ready for the solution. Okay, so the first thing I asked you to do is to create a list containing these elements. So the first thing you want to do is name your object. So you can name it anything you want. I'm just going to call it my list again. And my list is a list, and the first element is iris. The second element are the names of the columns in iris. So before we used names to extract the names of a named vector, but you can also use the same function to get the names of a list or the names of a data frame. So I'm just going to say names iris, and that's going to be a character vector of all the names of the columns of iris. Then we want the largest number in the first column of iris. So I can say max iris and give me the first column. And then we want the smallest number in the first column of iris. So min iris. So we've created the list, and then we're going to name the elements of the list. So I'm going to say names of my list is equal to this character vector. So the first element is the string my data, and then my names, my max, and my min. So now each element of my list has a name, and we can actually look at my list and see that each element is named. And finally, I wanted you to find the ratio between the max and the min. So you can say my list $, my max divided by my list $, my min. And you should get about 1.8. Another type of augmented vector are dates. So this is an example of the data being augmented in a way that's not exactly visible. It's something is going on under the hood. So what I mean is when you look at a date in R, it looks like a character string, but there's more going on underneath the surface that you can't see, which allows you to do certain things like compare two dates or subtract one date from another date, stuff like that. So let me show you. So here we're creating a vector called my dates, and these look like dates, right? It looks like December 31st, 2021 and October 31st, 2022. But when we ask for the class of this object, it tells me that it's a character vector, and that's not what we want. We don't want character, we want dates. So I'm going to use a function called as.date to convert these values to dates, but we need a little bit extra. We need to tell it what format the date is in. So this is how you do that. So basically I'm saying first comes the day, followed by a slash, then comes the month, followed by a slash, and then the year. Notice the year is a capital Y. That means it's 4 numbers and not 2 numbers. So after I run this and I ask for the class of my dates, it tells me that it's date, which is awesome. So now we can take the second date and ask, is it bigger than the first date? And the answer is yes. We can subtract the two dates. So I can take the second date and subtract the first date, and it tells me that the difference is 304 days. Or I can take the second date and I could add 10 days, and it tells me that 10 days after October 31st, 2022 will be November 10th, 2022. If you're dealing with dates a lot, I suggest you look into a package called LubraDate, which makes it easier to deal with date objects. So here's an exercise for you to try. Pause the video and resume when you're ready to see the solution. Okay, so the first thing I asked is, what date is 10,000 days after the first day of the year 2000? So the first thing we want to do is create a date object. So I'm going to use as.date, and I'm going to give it this string, 112000. And I'm going to tell it that the format is day, month, year. So let's see that that works. So here's our date object, and we can simply add the number 10,000 to this date object, and it's going to tell us that 10,000 days after January 1st, 2000 would be May 19th, 2027. Okay, so next, I asked you to create a vector of dates containing every day in December 2021. So let's start out by creating a character vector, and then we can convert that character vector to a date vector using as.date. So first we're going to use paste to create the character vector that we want. And basically every day, well, we know that the days are going to go from 1 to 31. So then at the end of each of these numbers, we can add a string which represents the month and the year. So we can say 12/2021. We'll tell it that there's no, actually we'll tell it, yeah, we can either say that there's no separator and then it will use the slash that we gave it here, or we can say that the separator is a slash and not put a slash here, and that would do the same thing. So we can stick this vector inside of as.date, and we can tell it that the format is day, month, year, and here's our vector of dates from December 1st to December 31st, 2021. So the last type of augmented vector we're going to be talking about are factors. We already saw factors a couple of times in this lecture. The species column of the iris data frame is a factor. But let's finally find out what a factor actually is. So simply put, a factor is the most appropriate data type to store categorical data. So each value is represented by a character string, but importantly, there's a known and finite number of values that that variable can take. So let me show you what I mean. Here I'm creating a factor, and I'm inputting a character vector, but it's converting it to a factor. So I'm saying, here's what I observed. I observed an A, then I observed a B, then I observed a C, then I observed another A, then I observed a C. So when we look at this object, we see these values represented, but notice they don't have quotes around them. So they're not character strings anymore, they're factors. So not only does it tell us the values, it tells us the possible values. So it's saying these are the levels of this factor. These are all the possible values that this factor can take. Factors are actually stored on top of numeric vectors. So if we convert our factor to numeric, we can see that A's are the number 1, B's are the number 2, and C's are the number 3. So this just relates to the order in which the levels are specified here. So the first level, all of those values will turn into the number 1, and so on. We could ask to see the levels of a factor just by using the levels function, and it's going to return a character string, which are all the levels. So similarly, how we used the names function earlier to either access the names or change the names, we can do the same thing with levels. We can either ask for the levels or we can change the levels. So here I'm using levels to say the levels of my factor is equal to this character string. So now it's changing those levels. They used to be A, B, C, but I'm changing them to X, Y, Z. So now when I look at my factor, we can see that the values have changed. So all the A's turned into X's, all the B's turned into Y's, and all the C's turned into Z's, or Z's if you prefer. A factor can either be ordered or unordered. So think about different data types that can either be ordinal or nominal. So like small, medium, large, that's an example of an ordinal data. When you're declaring a factor, you can say ordered equals true if you want that factor to be an ordered factor. If you leave that argument out, the default is false. So by default, factors are not ordered. And when you look at a factor, you see these little less than signs. That's telling you that this is an ordered factor. So there's some order to the levels. A is less than B, B is less than C. So here I'm declaring an ordered factor with other values. And when we look at the levels, it may not be what we expect. So like these values look like small, large, medium, extra large. So we might expect them to be in that order, but they're not. They go L, M, S, XL. Why is that? It also isn't the order in which they appear in. That might also be something that you think. So S is not first, even though it's the first one that appeared. So it turns out that by default, the levels are in alphabetical order. So that's what's happening here. So L is the alphabetically first level. So by default, that's the first level. We can change that. We can specify what order we want the levels to be in, which is usually what you want to do for an ordered factor. So here we have an ordered factor, and I'm telling it that here are the levels: extra small, small, medium, large, extra large. And then when we look at the factor, we can see that these are the values and these are the levels, and the order in which the levels appear in matters. Something a little interesting is happening. So kudos if you notice this, that there is a level that is present that actually isn't a value in the data. So there's extra small is a possible value, but it actually doesn't appear in this vector. And that's possible. Like there may be values that this vector can take, but that value isn't actually present in the vector. So here, these are the possible values that it can take, but not all of these values are actually present. The inverse is not true. So here I'm specifying this factor, this ordered factor, and I'm telling it that these are the possible levels that it can take. So notice that there are some values in the vector that are not possible levels that it can take. So S is not a possible level. So all of those values were changed to NA because this factor can only take these levels. So here's a final exercise I want you to try relating to factors. Give it a shot and resume the video when you're ready to see the solution. Okay, let's take a look at this final set of exercises. First, I ask you to turn the first column of iris into a factor. So we can get the first column like this, or any other number of ways that I showed you earlier. And we can assign it something. We can say it is now equal to as factor, basically the factor version of the original column. And then when we look at, let's say, the structure, we can look at the structure of iris, and we can see that the first column has changed into a factor. So now we have factor, 3 numeric columns, and another factor. So the question of how many unique values are there is equivalent to asking how many levels are there in this factor variable. And we can see right here there are 35, but we can see that in other ways. Like we can ask for the levels directly. We can say, what are the levels of this variable? And then, but more specifically, we want to know what is the length of this set of levels. And the answer is 35. So next I ask you to turn the species column into an ordered factor, where the species are ordered in descending alphabetical order. So right now, if we look at the species column, it's not an ordered factor, it's just a factor. But the levels are in alphabetical order, they're in ascending alphabetical order, which is, like I said earlier, the default. So what if we want species to be an ordered factor? We can say Irish $species is a factor of Irish $species. Ordered equals true. And then we want to specify what the levels are. So you can type these out by hand. That would, I guess, be a fine solution. You could say, you know, Virginica, then versicolor, and so on. But I think a better solution would be to use the levels function to say, I want the levels of this variable, but then I want to sort them. You can use the sort function to say, sort them in decreasing order. So let's just look at what this does by itself. So if I say sort this character vector in decreasing order, it's just going to give me a character vector in decreasing alphabetical order. And this is the argument that I'm using, the levels argument of this factor function. So when I run this, nothing is output because I didn't tell it to output anything. But now if I look at Irish $species, it tells me that it's an ordered factor where Virginica is less than versicolor is less than setosa. That's going to wrap up this lecture on vectors. Here are some references for you to peruse. My name is Jonathan with Statistics Without Borders, and I want to thank you so much for watching and have a nice day.